Sexy quantity.
You have to speak loudly, and it needs to be really quiet. We pick up a lot of background noise. Good morning, Dr. Jinnick and Katya. Welcome to Miller Creek Middle School. We want to thank you for your time today, and we especially want to thank Kevin here, our awesome IT person. Can we begin with anything you would like to tell us before we ask you our questions?
I would just say thank you very much for having us. It's a real pleasure and a lot of fun to have a chance to talk to you.
Excellent. Now we will start with our questions. We would like to do a couple to Dr. Jinnick, and then to Katya, and then Jenna, whoever would like to answer the question.
Okay.
All right.
Maybe before we go ahead, can you hear us okay?
Yes, very well.
Okay, great.
All right. So we'll start with Dr. Jinnick, number 1, and that was. All right, Isaac. Loud, say it slowly.
How did you first get into science?
I guess I was a very curious kid, like many of you, and so I don't have anyone who's a scientist in my family, but I read a lot of books as a kid, and I really liked watching science programs on TV and documentaries and so on. And I was just really fascinated by science in general. And then when I was in high school, I was really interested in chemistry. This was my favorite subject in school. So then I decided to basically do chemistry at university, and for a long time I knew that I wanted to do research. What in the end fascinated me the most was the chemistry of life, the chemistry of cells and so on. And so this is how I ended up doing biochemistry for my research. But it all started basically in elementary school, and then continued in high school. It really came out of total curiosity, just being interested in how the world functions.
Great, thank you very much. All right,
What's going on? Is it because I just saw the photo? I'm not crying. Look, I can blink.
Hi, thanks for the question. So before I became a professor in Switzerland, I actually worked for 6 years in California, in our own backyard at UC Berkeley. I don't know if you know. So I worked as a research scientist in a group that was headed by another professor, Professor Jennifer Dovna, and we were basically interested in how molecules can cut DNA in bacteria. And in the process of research on these DNA cutting molecules, we realized that there was this one called Cas9 that could be used as a tool for modifying DNA. And so I got involved because of this basically initial project on bacteria. So on things that had very little to do with what we would call now genome editing, but led to the development of.
Okay, thank you. All right, our next speaker, Jamie.
Actually, I think it's not hard to work in lab because I really like it, and okay. So actually, when you like what you do, then it's not really hard. It's just you have to be really organized in working in the lab and work clean, of course, that you don't contaminate the samples or whatever. And yeah, with the working time, it's very different. Sometimes you have to stay really long because your bacteria didn't grow or something went wrong. And sometimes you can't just go home when it's time to go home. You just have to finish experiments. And that's research, so it never really goes the way you expected. Sometimes it does, sometimes not. So, but I really like it, and I don't think it's hard. So if you like it, then it's fun.
Thank you. Our next speaker, Jaden.
Okay, so hi, I'm Jaden. And so this is a general question. How much does this process cost? We researched it, it's inexpensive, but all that equipment makes it look that very costly.
So yeah, yes, you're right. I mean, it's not cheap to do research, and we have to be very careful with the way we spend the money that we get, either from the government or from various research foundations on the projects that we do. It's really hard to give you a very concrete number, but I would say for a small lab in the United States, so someone, let's say a professor having a few people in the lab and working on a project, it takes up to, I would say, about $1 million to fund a research project that goes on for 4 or 5 years, something like that.
So it's not inexpensive like we read. So you can't believe everything you read.
Well, it is expensive, and things that take a long time will be expensive just because of the number of years that it takes sometimes to complete the project. So the costs will be high, but it really depends on what you do and so on. But it's not cheap.
Thank you. All right, our next speaker.
All right, that's another great question. Thank you. So what we do is really we try to understand how these DNA cutting molecules, Cas9 and others that are similar, function. And so what we do in the lab, we investigate the structure of these molecules and how basically the structure of these molecules allows them to do the job that they're supposed to. So it binds to a molecule of DNA and then cut it in the right place. And so this is what we're working on in general. And the reason why we do this is not only to understand why these molecules work the way they do, but also to then try and use this information to develop the technology to make it better, to make it more efficient, to make it safer for applications, for example, in medicine.
I'm Mia, and I have a question for Dr. Nick. What do you personally see as the pros and cons of CRISPR?
The pros and cons. So the pros are, it's a very relatively easy way of doing genetic modifications in organisms and in cells. It's fast, it's very precise, it doesn't cost as some of the other methods that have been used previously, and so in itself it's a really, really revolutionary tool. The cons, I would say that depending on what type of modification you want to achieve, there are some that are still not possible or very difficult to do in this method. So that's one of the cons. And the other is that sometimes it's not as precise as you would like to have it. And so you have to basically be very careful about how it's applied and what particular modification you want to make, because sometimes it can have side effects, essentially. But this is something that a lot of people in the field, a lot of scientists are basically working on right now to improve the efficiency and also the safety of the method.
Why does the lab have to be so cold when making the protein? I think
So actually, in our normal labs, it's not that cold. It's just with one cold room, which is 4 degrees Celsius, which is I think about 40 Fahrenheit.
Yeah, it's quite cool Fahrenheit. Yeah.
And for the proteins, they're breaking down over time. And to slow down the process, you just keep them cold. It's like when you keep your milk or your fruit in the fridge. It's also to make sure that it doesn't get bad. So it's just that reason. And that's why we sometimes have to freeze ourselves. Yeah.
So you mean the whole process that we showed you in the video? Yeah. It's kind of difficult to give an answer to a question like this, but because it really depends on the specific project that we work on. But if we were to say, you know, if you work on let's say if you try to determine the structure of a protein molecule, something like this, then it can take anything from 3 weeks to 3 years. That's part of the, it's part of why science is so beautiful. Sometimes it's very unexpected. It's you don't quite know how things are going to work out in the end. And sometimes it takes a long time, sometimes it does not. But it's really anything between weeks and years. I mean, most of the projects that we have in the lab are designed to last several months or several years. Yeah. Hi.
Would you use this process on yourself or your children?
That's also a very good question. I think if there was a medical reason, then I probably would. I should maybe say first of all that genome editing using CRISPR-Cas is something that has not really been used in humans as we speak, but this is something that will probably happen in the next few years. But I think it's something that you would have to have a very good medical reason for. So let's say a genetic disease, a hereditary disease that could not be treated in any other way. And I think this is where a lot of the development when it comes to human applications will be, because this really should give us the power in the coming years to treat some of the diseases that until recently have not really been possible to be treated.
Alright, thank you. Our next speaker. Yeah. Hi, I'm Samantha, and this is a question for Dr. Jennett. How exactly is Cas9 inserted into the organ?
All right. Thanks, Samantha, for the question. So I would say that very basically there are two ways of doing it. There are multiple, but there are two basic ways, depending on what organism or what type of cell you work on. So for some organisms, for animals, for example, the process of genetically modifying them actually starts when the animal is actually a single cell, so a fertilized egg. And for many animals, these cells are actually quite large. I don't know if you've ever seen fish or frog eggs in your science classes. Have you? No. Yeah. So some of these cells are big enough to see with the naked eye. And with these cells, you can actually deliver Cas9 just basically sticking a very fine needle into the cell and delivering the protein essentially with a syringe, like you would, if you were injecting someone. So that's one way. That only works, of course, if the cells are big enough to be handled in this way. The other way that's commonly used, and this works very, very well for cells that we can grow in the lab in a dish, is to actually deliver the Cas9 protein with an electric pulse, essentially giving the cells an electric shock. And this is basically because every cell is surrounded by membrane. And you can use the electric pulse to temporarily disrupt the membrane, to make it leaky, if you will. And that essentially helps the cells to then take up the protein. And after a while, they're fine again, basically. But if you give them an electric pulse, they will do this. So either injecting or electric shocks. Those are the two most commonly used ways.
And don't mix it up.
No. Okay, our next speaker.
She stood up. Wow.
Hi, I'm Jada. I was wondering, what is your favorite? Oh, this is for Katya. What's your favorite part about working in the lab?
Okay. Actually, the thing is, I never wanted to work in an office where you do every day the same stuff, and that's why the lab work is perfect. So you do every day something different. It's a really long process from the DNA to get the protein, and it's always something different. Then, of course, things always go wrong. So you have to think. You have to make decisions. What can you try? What can you do that the protein is happy? And it's never boring. So that's why, or that's what I like most. That I do every day something different, and also I take care of the students when something is going wrong or when they need something. So it's like really being the mom of the lab and take care of everybody and that everything is working. So there's a lot of different things to do, and it's actually the best part.
Hi, my name is Grace, and my question is, what do you see as the main uses for CRISPR/Cas9?
Well, there are lots of different uses. So first of all, for us as scientists, it's really a wonderful tool with which we can basically study how genes function in different types of cells and different organisms and so on. So one thing is, of course, this side of it being a tool or a method to use in scientific research. The other use, which I think will become very important in the coming years, is its applications in medicine to either treat genetic diseases or hereditary diseases, or to basically help people in medical research develop new drugs or develop new systems for testing drugs. So, for example, generating or making cells that you can use as an experimental system for a certain disease that you can then try to develop drugs against. So this is going to be one of the main uses of this in the future. There are others in biotechnology, so in modifying plants or animals in agriculture, or in the production of, or modifying microbes that would be for the production of different substances, chemicals, either medicines or biofuels or other things. And so there are potentially many different uses, but I would say medical applications, research applications, and biotechnology would be the three main ones.
Thank you. Hello, my name is Charlie, and this one is for Dr. Minnick. Once Cas9 does its sniffing, how does it know when to stop? How do you take it out, or does it self-destruct?
All right. Thanks, Charlie, for the question. So the short answer is that Cas9 actually doesn't know when to stop. But there are two things that sort of put a brake on its action in the cell. One is that cells continuously recycle their components. So they keep making proteins, but they at the same time break them down over time. And so Cas9, like any other protein, will eventually be broken down by the cell within about 24 hours. And so that's one thing that basically limits how long the protein stays active in the cell. The other thing that limits how long it's active is the modification that it does to the DNA, meaning that it will cut the DNA until the DNA gets modified so that it no longer is recognized by Cas9, and then that's the other reason why it then stops working.
Hi, I'm Natalie. What advice would you give to kids who weren't sure about what they wanted to do when they grow up, but really loved science?
That's another great question. So I would say, there are lots of things that you can do for jobs or for your career if you're interested in science. And so, even if you don't know what to do right now, doing science or being interested in science is going to be very helpful, and it's going to be very important. So I would say, if there are, read a lot, be interested, be engaged. There are lots of great programs on TV. There are lots of great programs on the internet that one has access to about science. If you're interested in research, then I would say try to talk to people who can give you some ideas. Talk to your teachers. Very often they know people in research who could give you advice. Through your parents. I don't know if your school has a science club. Do you have a science club?
We have a classroom with science, so I guess it's science class.
We have a baker's school.
Yeah,
Oh,
so
it's got one.
there are all sorts of things that
We have like a
you
room
can
full
do,
of
and
science. Called the science
you know, the more the better.
Ryan told me about it.
And I would say it's okay if you don't know what you want to do for your job, but the important thing is stay interested. At some point, you will have a better idea of what you want to do, and all the science stuff that you have learned will be very useful for that.
We have 2 more speakers.
I want to be a bus driver.
So actually, yeah, it took about a week, and I worked a couple of hours today and then to optimize everything. But I started already, I think, in January to collect pictures and to take some videos, and I had to go through all the party pictures we have and from our retreat or kind of class trip in Italy, which pictures are nice and which I can show 12-year-old kids. And it's, yeah, it was kind of worth several months to just get everything done.
But about a week, it took. Yeah.
Well, we'd love to thank you very much for taking your time to do that. And now for our last speaker.
Oh, I was gonna be that.
So we don't really work on humans. This is something that you know, you can't just do like that. So you know, there are very strict rules about what you can or cannot do when it comes to doing experiments on humans, and so this is something that we do not do. We work mostly on other organisms. What we do work with, however, is the cells that originally came from humans a long time ago. These came from, for example, cancer cells that were at some point taken from a human patient and that have been used in the lab for a long time. So this is pretty much as close as we come to a human. Is essentially a dish with cells growing in it in an incubator. But we don't really work on living humans, so to say.
Well, that is all of our questions. Unless someone else has one that we
Oh,
haven't
oh.
asked.
No, I'm not. We're heading to no, Matt. What you said.
Could you please repeat the question? Sorry, we had trouble hearing you. Oh, who funds it? Ah, okay. So again, it depends on where you are. Country-wise, here in Switzerland, we have a national science foundation, which is basically government giving funding to research groups or institutes at public universities. In the United States, the research is funded by many different sources. Some of it is funded by the National Institutes of Health. So again, this is the federal government that is funding it. Some of it is from various private foundations. One of the leading ones is the Harvard Medical Institute, for example. in the early days, and I think they still continue funding the Bill and Melinda Gates Foundation is funding research on CRISPR. So it comes from a lot of sources in general. Next time.
Do you think there are any dangerous applications of CRISPR?
Dangerous applications. I mean, it's something that is mentioned a lot in the popular media. Yes, you could potentially think about doing bad things with CRISPR, but I don't really see a reason why would people want to do that. I think there are other ways that would be probably a lot easier to do. I tend to focus on the good applications and on the beneficial use of this technology.
Wait, Hunter, how's it?
One more question.
No, I don't know. Raise your hand. Raise your hand.
She said class.
What are all those things in the back? Like, what are all those judges and stuff in the back?
Essentially just bottles with solutions that we use for various methods that we use in the lab to either purify proteins or purify DNA or do experiments. They're essentially just chemicals in water solutions, in aqueous solutions.
They love the song. They go around campus now singing. Should we do a few bars?